the architecture behind that. Basically, in case that wasn't clear, the system that Skynet uses, BOINC, is actually a kind of open framework for scientific computing, distributed scientific computing. And I just thought I'd give a quick overview of how to set up under Linux. I think a lot of people often don't run things like SETI at home or Skynet or whatever because they don't want it to make their serverless responsive, say they're going to start at home or something like that. So what I've done in the past is actually run BOINC projects just with a high NICE value so that you can, or low NICE value, or whichever it is that gives the processor the scheduling priority. So if you've got like a Raspberry Pi at home or a server or a rack or something, you can have that running consistently. Any services you've got on there, like a web server or whatever, will be, their responsiveness won't be affected at all by it. So it's a good way to do it. And particularly, I think a lot of people in this room might have a Raspberry Pi at home or something like that they're not really using. And things like that have a low power draw, so you can just run that at load with Skynet or whatever all the time, and it's a good way to get started with a project like this. So there's just some notes on just how easy it is to set up. Both in Raspbian and Arch Linux, you can install BOINC just with apt-get or with pacman. You can either start it with init scripts in Raspbian or with systemd in Arch. Systemd enable BOINC. This is, if you are running X in either of them, you can run this BOINC manager tool, which gives you a pretty decent interface when you first start up. It'll even let you configure the project from scratch, so you can select from a pretty big list of different projects that run on BOINC. If you're running the shell, you just run a few commands to create an account for a particular project. This is an example I stole from the SETI at home website. That's the search for extraterrestrial intelligence. I think BOINC actually came out of that project. I remember I ran SETI at home like 10 years ago, but
yeah,
I thought it wasn't
SETI at home was like a standalone app.
Yeah.
And eventually they talked to virtual people and decided that they were the universal platform of these sorts of programs. And now, SETI at home, Folding at home, Limestone at home, the Skynet obviously are all using the same system.
Yeah. And yeah, you just create an account, you get your account key based on your address and password, you attach to a project with your key, and it just runs. This is an example of the systemd service that runs it. This is the one that actually came with my distribution that my Pi runs, which is Arch Linux. You can see here systemd supports setting a nice value for the process. So as long as that's there, whatever else comes in that wants to use CPU on your Raspberry Pi is going to get better priority, and it's not going to matter. Alternatively, with systemd, you can use the CPU shares thing, which configures the C group to have a lower or higher than default share of the CPU. And just in case anyone didn't really know about BOINC, there's some other pretty interesting projects you can run. You can run, I think you can run any number of projects in the same BOINC instance or through the service. So there's Rosetta at home, which simulates protein folding for disease research. Hydrogen at home for hydrogen storage research to do with clean energy. Mind modeling at home, SETI. They're not all called at home, but it is a pattern, I guess.
Yeah, the BOINC client allows you to attach a bunch of projects and then determine the scheduling and what things like how much CPU, how much whether it's going to run while idle or not idle, and then you can set the time that it will take between switching between different apps, and you can weight them. So if you want the Skynet to get 70% of CPU time and SETI at home to get 30%, you can do that as well.
Yeah. So yeah, I think it's a lot cooler than running a system at load to mine for bitcoins or something. And the one nice thing about it is you can install it, you can set up the projects and then leave it without even going to the websites of like SETI or Skynet. And then a few months later, you can actually go and look at the web front ends that the projects run and see what you've done and compare between projects, the impact you've had and stuff like that. Thanks. Cool. Instructions, I tweeted it with the Astronomy Miniconf hashtag.
things. I got a bunch of brand new servers in my job, and I went, right, okay, I've got all these brand new servers, unknown, I'm going to, heat stress relieve them somewhat. I'm going to run DNetC and, make them do something. And then after a little while, I found a lot of this BOINC stuff in the SETI at home, and I thought maybe I could be doing something more useful than, just cracking RC5 stuff. There's got to be, more useful things out there. And eventually I found the Skynet, and so it's a browser-based thing. And eventually they released a Java client for the Neris, is it coming up? Yay. All right. So eventually I got the Java client running in Linux, and I had a few cores sitting on a box at home, and I thought, okay, maybe I'll move this to my server boxes at work. And while these boxes are in dev and they're doing nothing else, I'll get busy. No, that's the wrong one. What have I done with it? Here we go. Okay, so first part of this is how I got 50 million credits on the Skynet. So I've got 12 servers with 24 cores and an awful lot of free time and waiting for lots of things to happen in my job, and these machines are sitting here idle. And so eventually when I sort of came back to it, I realised, hey, this is crunching rather quite a lot. I spent a little bit of time and effort trying to get it all working rather nicely. And so then they started issuing some challenges about how, let's see if I can make that work better. Is that doing it now? Yep. All right, so there's this lovely little table here of everyone's got their login and how much credit they've got and whatever else. And so I spent quite a lot of time sort of optimising. Yeah. So I just got my ham radio license and I was really excited and I was naming everything after my call sign, So, but I spent quite a lot of time trying to figure out how to make the most of the Java client and keep it running, and it was really manual, and I had 240 cores. I was trying to keep processes running and stuff. So I ended up scripting lots of things away, and the whole process was, pretty tedious. But after a while, I got things all sorted out. And then after a while, they started issuing some challenges, and there was more interesting stuff coming on the community, and they were announcing more stuff in there. And so I was actually really quite excited about the whole idea. And then I started reading more about radio astronomy, and because I'm doing ham radio, and this radio astronomy is it's quite similar in many regards. You've got radios, you do receivers, your antenna systems, you've got all this cool stuff. And then I started catching up to other participants in the thing, and then there was this big prize offered, and they were talking about what the 1 year anniversary thing was going to happen, and there was going to be some prizes, and I thought, okay, I'll put some effort into and try and keep everything up and running, and I wrote a lot more code to keep things going, and I came out doing quite well. So, but this is a Java. I was doing all my work in the Java client on Linux boxes, not in a browser. You can open a browser and create one process and contribute. I was contributing quite a lot, so it's really cool that you can actually put back into a community that actually does something, because RC5 cracking keys is kind of pointless. And it's still like one of those things where, SETI at home, it didn't really have a lot of appeal to me, but the radio astronomy thing I thought was actually really quite cool. So, come the 1 year anniversary of the Skynet project, I got a very exciting email saying, would you like to come and see the SKA site? And I just about fell off my chair when I got that email. So yes, it was it was really, really cool. Where is this? Okay, so I basically came over to Perth, landed in here and went and talked to the folks at ICRA, and we drove 10.5 hours up to Murchison. And it was a very long way, but it was absolutely worth it. So this gives you an idea of that red dust on the site. And these are a couple of the dishes. These are the dishes at the very middle of the ASCAP site. So these dishes are 10 metres across. So it kind of gives you a bit of a scale of what's going on. What else have we got? Oh, that's accommodation. So everyone gets around like this. Every little vehicle has little yellow stripes down the side. It's very, very different to what you're used to, driving around. Flat tyres. Bloody hell. So this is a view from near that hut, the engineering hut in the middle of the MWA. You can see how red everything is. They talked about the breakaways. There's that little plateau there. And this is what was called to me, was described to me as the graveyard of the antennas. And so this must have been the original prototype array, yeah? So these are a bit different shape to the current ones that are there.
It's harder to work it all in.
Pardon?
They're actually the new shape, I think. All of the old shape ones got thrown away earlier.
Well, this is the end of 2011. So this was the old set, and the new set was already in when I was there. So.
There was an even older set that disappeared in like 2009.
So this is people busily working away in that engineering hut. And this is a receiver there, which is about to be deployed out into the field. So up the back here, this chap up here was he was an astronomy researcher. We had some of the folks there from ICRA, but there was an astronomy student there was describing to me, giving me the backstory of lots of things. And so you'd hear various buzzwords and lots of abbreviations, and he would go, oh, that means, blah, blah, in the background. So that was really, really quite interesting. Where are we? Oh, okay. So this is in that data center that we're talking about. And so on the door, we saw that big door before. This is the double. So there's two layers here of the fingers in the door to actually earth everything and make sure everything's shielded properly. So there's a data center, loads and loads of racks. At that point in time, we're all empty. But up the back here, there was just, I don't know, thousands and thousands of fibres that were being run from the big dishes, from the A to D converters of the dishes, back to the data centre. And so to keep that RF noise down, the A to C, so from the telescope, you're bringing the analogue stuff down into a digitizer, and then it's running over fibre back to the data centre. There's another view of that door. Dishes. Okay, so you have the dish at the top there, and in the bottom here you have what they call a pedestal. And in there you have all of the coax coming down from individual little patch antennas on the top of the dish, coming back down in here, and they're patched into, I'm not sure how many. And these are 188 cables, I think, coming down into this patch, which then go into ADCs, which then go digital off.
So what that is at the focus of the ASCAP dishes is what's called a phased array feed.
Yep.
And they actually do in digital what we do in analog. So we have those delay lines.
Yeah.
They sample basically all of these little antennas and then form beams, multiple beams, 36 of them, I think, in each antenna. So they've got more compute associated, I think, with each of their antennas than we need to do the correlation on the MWA.
Which is why it's a significantly more expensive project to have been built. Yeah.
What they win by is they have one 10-metre dish that is looking at 36 places on the sky at the same time.
Yeah. Because the focus is different for every little point on the top.
Well, it samples the whole focal plane. So instead of just being at a point, they shift it down a bit, it samples the whole plane. And they basically generate 36 individual beams. No one's ever really tried to do it in an astronomy context before. So it's a lot of new technology in CSIRO.
Okay.
And it's why it's taking so long for people to get it to work.
So there's a couple of these motors to turn things around, move the dishes side to side. There's actually quite a lot of power goes into actually moving around just a little 10-metre dish like that. So I went and visited the Parkes dish and sort of stood there for about an hour thinking about how much that thing weighs and how much energy you've got to put in to move it around. And when I saw this, I thought, that's a little motor about yay big, it's a couple of kilowatts. How big is the Parkes dish and how many tens of hundreds of kilowatts? Hey?
Surprisingly small.
Gearing, eh? Yeah.
Interestingly, the Parkes dish, obviously, being involved with the Canberra Deep Space Centre, I have to point out that it's not quite as big as the one in Canberra. But a lot of this is done just by reducing friction as much as possible.
Yeah.
DSS 43, which is the big dish, the 70-metre dish at the Canberra Deep Space Centre, it's 4,000 tonnes, the whole thing, but it floats on a fraction of a millimetre layer of hydraulic fluid, and once that's happened, it's got a few, tens of horsepower motors that just push the thing around really, really easily. So yeah, it's all hydraulics and friction reduction.
Okay.
It doesn't move quickly, but it moves easily.
Yeah. So you're feeding a lot of coax from a dish that moves, in a plane that moves, down through these lots of trays in order to get the coax down and inside the building. So they have a manual, and obviously these things are all automated from the control centre, but there's a manual box for every little dish, and so you can control each of the degrees of freedom in there. So this is this is pre the correlators in the I can't remember what this one is. I think this is where all the coax comes in from the dishes into where it's actually the A to D converters in the hut. This has all changed since I was there, and they've centralised this all in the either all in the pedestals, or they've moved it all to the data centre. But there was a little hut here which did the initial testing for a whole bunch of the ASCAP dishes, and so part of that is yet another rack with some storage and some compute for doing that same reduction of data down to the useful parts. And this is what they call the correlators, which is the custom hardware, which then takes all that data and makes it into a more useful. I assume it does all the FFT and stuff. Okay, so this is from the MWA, as they were doing the calibration testing for a whole bunch of the tiles. If I zoom in a little bit.
So I take it each one of these is what you're talking about.
Each one of those at the top.
So we've got a receiver and a bunch of tiles, and you can see that little peak there is around 200 megs from memory. And so you can see the shape of these is a little bit different, and there's an X and a Y in each of those. So for each tile you've got an X and a Y, and so they're I believe they're summed for the whole tile for the X and the Y. And you can see there that some of these are quite different shapes because they can see different parts of the sky. So at that point in time, they're calibrating a lot of these, all of the tiles. What have we got happening here? Okay, so that's not very easy to see, is it? But we've got a Y channel and an X channel, and so you can sort of see the same spectrum across each of those, and they're somewhat slightly different shapes. I stopped taking photos for a while because I was listening to lots and lots of descriptions. All right, so that was the antenna graveyard from the previous ones, but that just gives you an idea of these broadband, the dipoles. So the little insulator here at the bottom. I'm not sure what's going on there. Oh, okay, so that's the bottom of one there, and then that's another one behind it, so you can see the insulator on the other side, but there's an earth strap there and stuff. So that's the centre in there that goes into the LNAs in the middle. So to each tile, we have an X and a Y cable that goes out from the receiver. I don't know, just another shot of the tiles. Oh, and this is the receivers. So I assume that each of the tiles comes back to a receiver has an exactly the same length cable, and the spare is stored on the spool?
We've got 5 or 6 different lengths of cable, but we wanted to try and keep it to a minimum number of different lengths. So
Yeah.
That's what
Okay, so
it also says re-terminating the cable after you drag it back to the receiver.
So yeah, there was quite a few of these spools sitting there with all the extra cable sitting on.
A lot of fibre optic buried in the ground.
Yeah. I don't know if I've got any photos of that. So a lot of this particular lot were all created by the students, I believe at Curtin at the time. And, the human side of this was number 1969, and it's got Apollo 11 written on it and an eagle, So this is for me the human side of the whole project. And, the humour and the people there, it was just a lovely touch to see all the other little bits and pieces going on. Actually, I was really quite interested in this. This is the timing syncing to keep all of the receivers so that they're capturing frames at all exactly the same time. I can't remember exactly what the pulses were going on here, but this was going out, was it 655 megs? Or no, 16 bits.
5.36.
Yeah. So, I was learning quite a lot as I was going through this because, I was thinking from a ham radio perspective and going, okay, what am I going to need? What can I learn from this? Because there's so much going on at different levels and syncing time from GPS and all that sort of stuff. Okay, so this is actually back at Curtin, and this was the one of the prototypes, and more prototypes, I assume. There's a whole bunch of these antennas there on display. So, and I assume this is sort of like the prototype for that Christmas tree one that Kirsten was talking about. And more prototypes. Why did they choose, to make things in this particular way? Do you guys know?
It's made by Italians. It's called the Valve.
It's got a bit more flair, has it? Goes faster. All right, so this is a photo I grabbed from somewhere, and so this shows those Christmas trees that Kirsten was talking about earlier. Bother. So you can sort of see that it's quite similar to that sort of shape thing. Where are we? Anyhow, what have we got here? Oh, that's that data center, which we saw before. Okay, so so this was sort of on the northwest side. The sunset was over here. It was really beautiful. One of the guys from ICRA did a whole bunch of time-lapse photography, and there's beautiful shots of the stars going over and whatnot. And so this is has that breakaway on the end of it there. So it was actually a really, really exciting journey up and back. And it was a week of 40, so it was, we really had to work for it. So cool. Thank you very much.